Welcome to this video on independent and dependent events. By the end of this video, you should be able to use a two-way table or Venn diagram to model a chance process and calculate probabilities involving two events. You should also be able to calculate and interpret conditional probabilities and determine if two events are independent. So this is day 2 of Taco Tongue and Evil Eyebrow. I'm using the data from a previous day. So at this point, what I really want you to do is I want you to pause the video and I want you to answer questions 2 through 4 completely on your own and then come back and see how you did. Alright, so for question 2, find the probability of yes Taco Tongue or yes Evil Eyebrow. Remember the word or means we're going to add them together. So the probability of yes Taco Tongue is 27 out of 31. Or yes Evil Eyebrow is 10 out of 31. But remember, this happened in the last video when we talked about this. If you're going to, we counted this way and we counted that way, and we ended up counting those 10 people 2 times, and we don't want to have that happen, so we're going to subtract off the overlap. It just happens to be that same number. It's not always. And we get 27 out of 30. And so yesterday we called that the general addition rule for not mutually exclusive events. So let's write that. So we have the probability of A or B equals the probability of A plus the probability of B. And then you have to subtract off where A and B happen, where they coincide together because you've counted them twice. So you take off the probability of A and B. All right. So let's take a look at number 3. Given that the person selected is a yes Evil Eyebrow, what is the probability that they are a yes Taco Tongue? Write as a fraction, a decimal, and a percent. So given that they are yes Evil Eyebrow, that means you divide by the yes Evil Eyebrow number. Of those 10 people, how many of them are yes Taco Tongue? Well, all 10 of them are. So that will be equal to 1, which is that happens 100% of the time. Okay. Then we have number 4 that says, given that the person selected is no Evil Eyebrow, what is the probability that they are yes Taco Tongue? Write as a fraction, decimal, and a percent. So given they are no Evil Eyebrow, so no Evil Eyebrow has 21 people in it. Of those 21 people, who is yes Taco Tongue? 17 of them. And when you divide that down, I got 0.81, which is equal to 81%. Now, we have a definition here that if two events are independent, if knowing whether or not one event has occurred does not change the probability that the other event has occurred. So I'm wanting to know, are the events yes Taco Tongue and yes Evil Eyebrow independent? And then I need to be able to explain. So if they are yes Evil Eyebrow, 100% of the people are Taco Tongue. If they are no Evil Eyebrow, 81% of the people are Taco Tongued. So if I know somebody is yes Evil Eyebrow, I know they're Taco Tongued automatically. So it changes if the second part, I know about their Taco Tongue. I know something about it based on whether they're yes Evil Eyebrow or no Evil Eyebrow. And for that reason, they are not independent. So no, they're not independent. So people who can Evil Eyebrow. So this is my explanation why. I answer the first part, are they independent? Now they explain. People who can Evil Eyebrow are more likely to Taco Tongue. So people who can Evil Eyebrow, I'm just going to call it EE, are more likely to Taco Tongue. All right, let's add a few more notes into this. We got this answer no because we looked at these two percentages and we could see if they were yes evil eyebrow, it's 100%. If they're not, it's only 80%. So that helped us answer this question. And we said no because the probabilities are not the same. All right. So when we did these two problems, 3 and 4, we had givens. Whenever we have a given, that is something called a conditional probability. Okay. So we had to meet some sort of condition, and that's what we were dividing by, the condition. And out of those people in that condition, that's how we got our top number. Now there's a particular way to write the probability symbology here. So we're going to write it, so the probability of yes taco tongue given, so that big line, I write it probably bigger than you'll see in your textbook, means given, and anything that comes after it is the given, the condition, given that they are yes evil eyebrow. So yes evil eyebrow. Okay. So the yes evil eyebrow there, that's our condition. All right, let's try it again for no evil eyebrow. So given that the person was no evil eyebrow, so given no evil eyebrow, that's your given, that's your condition, right? What is the probability that they are yes taco tongue? So we're looking for yes taco tongue divided by no evil eyebrow, which is exactly what you already did. You already know how to do the math here. I'm just giving you the more formal symbology that you'll see in textbooks and possibly on tests and quizzes and stuff. All right, so let's flip this over and let's try the back side. All right, so here we have data for a whole lot more people. This is for 600 people, and we want to find the following data. You should be able to completely answer 6 on your own, and then come back, check your answers, and I'll get you started on 7, and you should be able to finish it out on your own. Okay, let's see how you did. So yes taco tongue. So yes taco tongue was 480 people out of the 600 total people. So that was 0.8, which is 80%. All right, so now I've written this as a condition. There's your given line. Given yes evil eyebrow. So given yes evil eyebrow, that's 200 people. Of these 200 people, how many have taco tongue? 180 of them. Okay, and I got 0.9, so that's 90%. Right here we can already see we have some different probabilities going on. Let's see what happens when we do our third conditional. Okay, so I have given no evil eyebrow. So no evil eyebrow is 400 people. Of these 400 people, how many are yes taco tongue? That's 300 of them. Okay, we're going to simplify that down. I got 0.75, which is 75%. And again, we have different probabilities. That means if I told you they're no evil eyebrow, you see that they're less likely to taco tongue. Okay, if they are yes evil eyebrow, they're more likely to taco tongue. 90% of them did this. So are they independent? No, they are not. All right, so let's look at the table in 7. We want to make the table as if the events are independent. And so we got 80% for taco tongue up here. So what I want to do is I want to have taco tongue be 80% of the numbers. and the no, or so really it's going to, and then if that's 80%, this is going to have to be 20%, so we have 100%. So we have 200 people in this category. If 80% of them are Taco Tongue, that means there's 160 of them. I want you to go ahead and finish filling that out, and you should be able to get through number 9. Pause the video, come back when you're done, and let's see how you did. Okay, so let's see how you did. We're going to start back over. So we had 160 there. There was 320 in this section, 40 here, and then 80. All right, so the probability of yes Taco Tongue is still 480 out of 600, which is 80%. All right, so now we're having the probability of yes Taco Tongue given yes Evil Eyebrow. So yes Evil Eyebrow was 200. Yes Taco Tongue was 160. Now we just set this up to be independent, and we used 80% to find that number, so it would be weird if it wasn't 80% at this point. Okay, now let's look at the no Evil Eyebrow. No Evil Eyebrow is 400 people. Yes Taco Tongue is 320. That is also 0.8, which is 80%. Now, what did you notice about your answers in 6 and 8? So when we look at 6, I notice that these are not equivalent. Okay. So that's what I want to write in that answer. And when I look at 8, I notice that these are equivalent probabilities. All right. So that's really what we want to take and we want to write in there. All right, so I just took our notes from up here and I wrote them in there. So what we were coming to with this is, if you calculate probabilities and you're finding different probabilities based on what category somebody is in, then means they are not mutually exclusive. No, sorry, not independent, not independent. Okay. And if they are, it doesn't matter which of these categories, it doesn't mean any different. They are independent. Okay. So if A and B are independent, that means the probability of A is the same as the probability of event A, even though B has already happened, my condition, which is also the same as the probability of A, given that a different category, the complement of B, has already happened. They'll all be the same if they're independent. Okay? So think of it this way. If I flip the coin and I got 10 heads in a row, what is the probability of the next flip being a head? It's still 50-50. It doesn't matter what's already happened. It's still 50-50. So that is independent. It didn't matter what's already occurred. But if I had a deck of cards and I passed out a few of the cards, the probability of what's remaining in my hand changes because I now have a different amount of cards than the original deck. So the probabilities change, so they'll be different, and that is not independent. Hopefully that helps clarify it just a little bit for you. So let's go ahead and summarize this down and get our learning targets. All right, so first let's talk about the conditional probability. Now remember, you already know how to pull these numbers out of a two-way table and how to write this. Okay, so I'm giving you a formal formula for it. So we have the probability that event A happens given, remember the line is the word given, that B has already happened, is the probability of where A and B cross in the two-way table, the intersection, divided by the probability of B. All right, so this B, that's your condition. And the A, this is the intersection of A and B. All right, so you already are knowing how to do this. We're just kind of formalizing our knowledge just a little bit here. Now, the other thing I wanted to review is independent. So we actually talked about this in Unit 1 when we were making our stacked bar graphs, and we were trying to decide if there was an association between two variables, and if they looked pretty much the same, we said there was no association, but if one had a bigger percentage than the other one, we said there was an association. That's also independence. Okay, so if they looked about the same, they're independent of each other, because knowing one piece of information doesn't change what you know about the other. But if they were very, very different, knowing a category somebody was in would change your understanding because the probabilities were so different. So, independent. All right, so independent, when knowing one event has occurred or not occurred, so that would be B or B complement, does not affect the probability of the second event. It doesn't matter whether it happened or not. The second event is going to be what it is. It doesn't matter that we got 10 heads in a row. The next event is 50-50 heads or not. Okay? So what that means is if the probability of A equals the probability of A even though event B happened before, and that equals the probability of A even though event B didn't happen, if they are all the same, then A and B are independent. All right, what I'd like you to do, I want you to stop the video, and I want you to try the check your understanding all on your own, and come back and check your answers. All right, so the Pew Research Center randomly selected 100 mothers ages 40 to 44 in 1976, 1994, and 2014, and asked each mother how many children they have. The two-way table summarizes their responses. Okay, so suppose we randomly select one of the survey respondents. We define the events as C for having 4 or more children, S for 1976, N for 1994, and F for 2014. All right, so find the probability of 4 or more children given it's 1976, and then interpret. Interpret means explain. So the probability of 4 or more children given that it's 1976 was 40 out of 100, which is 40%. Given that the mother was surveyed in 1976, that's what that says right there, given surveyed in 1976, there is a 40% probability that she had 40 or more children. Okay, then we have, given that the mother chosen was not surveyed in 1976, what is the probability that she has 4 or more children? Write your answer as a probability statement using correct symbols for the events. So, not surveyed in 1976 would be the complement of surveyed in 1976, okay? And so what we're really talking about up here is these two. So you could have, if you didn't think about the complement of it, N or F could have been written right there also, okay? So we're talking the probability of 4 or more children given it's not 1976. There was a total of 200 women in 1976. There was 26 of them who had 4 or more children in not 1976. So they have a probability of 0.13, which is 13%. Okay. So are the events surveyed in 1976 and 4 or more children independent, and explain. So you have to explain your position here. So the events surveyed in 1976 and 4 plus children are not independent. Look at their probabilities. Mothers in 1976 were more likely to have 4 or more children than mothers not surveyed in 1976. Okay, that was my explanation. You could have said mothers not in 1976 had less children, were more likely to have less children. Some way of indicating the relationship is being based off of when the survey occurred. And then this is, I went ahead and used this symbology because if they were equal, they're independent. So I put a not equal, so that makes them they're not independent. All right, hopefully that was helpful. If you have any questions, let me know. See you in class.